everyone. So we're moving on to the next topic. This entire unit is all going to be about forces. So we're going to kind of switch gears. We're still going to have some stuff about linear motion going on, but we're again going to be focusing more on a different set of equations. So we're going to talk about Newton's three laws, and the bulk of this class will actually focus, or this unit will focus on these three laws as well as friction. Now, the first law, most of you should know a lot of these laws from going through this stuff, but these laws came about through Isaac Newton. You probably heard the story. Isaac Newton was sitting underneath a tree, an apple falls on his head, and he wonders, what caused that? There was a lot going on in that story. There's other accounts that he was considering why the moon actually travels across the sky, and he came up with all these different laws of motion, which to this day we still use to kind of describe the motion of everything. In fact, Newton's three laws are linchpins to many of the other equations that we end up learning. So, a lot of the other topics with momentum, energy, all these things, they're all kind of derived from Newton's three laws. Because of this, because this ends up being the literal foundation for this course, we end up actually calling this entire topic of physics Newtonian physics. Uh, this is in contrast to things like quantum physics and general and special relativity physics, or string theory physics, all those types of things. So Newtonian physics is more kind of like what we would experience in our everyday lives. All right, so the first law, like I said, all three of these laws you've learned at some point. The first law is very straightforward. It starts off with discussing why objects actually move, and what is necessary in order for them to do it. Now, it's split into two different parts. The first part says an object at rest tends to stay at rest unless acted upon by an unbalanced force. And the second part is an object in motion tends to stay in motion, moving in a straight constant velocity unless acted upon by an unbalanced force. So to put this in simpler terms, Newton's first law is basically saying objects will keep doing whatever they're doing. They're stubborn objects, and that the only way you can change the motion is if you force it to. For example, if you see a ball sitting on a table and it's not moving, all of a sudden flies up in the air, you know that something had to have caused that to move. It just didn't naturally do that. So that's pretty much what this first law is saying. Um, yeah. Now, this actually is a lot of times called the law of inertia. The reason being is inertia is being used as a descriptor of how stubborn objects are or how resistant an object is to this change in motion. So the higher the inertia, the harder it is to change the motion of this object. The more force is going to be required. For example, if you think about moving a boulder versus a paperclip, the boulder requires a lot more force to push, therefore, it would have more inertia. For example, another example, if you had a baseball rolling towards your foot and you had, again, a bowling ball rolling towards your foot, one of them it has more inertia, the bowling ball. Therefore, it's going to be much more resistant to changing its motion. It's going to kind of ram right through you and end up hurting your foot without really deviating when it hits, while the baseball, when it kind of hits you, it's going to bounce right off fairly easily. So, all in all, inertia is just a really fancy way of saying mass, and that's the big thing. So, the moment you see the word inertia, you should immediately cross the word out and write mass, because this comes up so much where they say which of these objects has the greatest inertia, and you have to pick mass. This becomes extremely important once we talk about momentum, because the main way that they're going to try to confuse you is they're going to give you more information than just the mass, expecting you to find something else like energy or momentum. but you have to remember inertia is mass. Mass is inertia. Keep repeating it to yourself. If you want, make a little flashcard. Have that be on one of the flashcards where it says inertia, and you immediately say it's mass. And this is the main reason why we have wrecking balls being used to demolish buildings, and or why anvils are used in order to actually bend metals. If you've ever seen someone who does blacksmithing, like on YouTube, they have these gigantic metal heavy anvils, and the main idea is because every time the person swings down with the hammer onto the metal that they're working with, if they were hitting it on a somewhat light, light object, a light table source, every time they hit down, the whole thing will kind of move up and down. So they want something really heavy so that the force that the blacksmiths exert onto the metal will not actually move the table. And again, same thing with the wrecking ball. You have this gigantic, high inertia object. You start swinging it, and it has so much inertia, and it's so resistant to changing its motion that even when it comes up against a wall, it just plows right through it and continues on in its straight motion, because objects in motion tend to stay in motion, and that wall will not have enough force to change the wrecking ball's uh, motion because of its high inertia. There's a YouTube video that I like showing. It's an old ad for H&R Block, basically showing that, you can watch it yourself, but it kind of deals with the whole wrecking ball and inertia thing. All right, so again, inertia is just a fancy way of saying mass. The more mass an object has, the more inertia it has. Now, this is actually pretty much the reason why when if you ever fill up your car, like if you put something on the roof, or even if you have something in your seat while you're driving, as I'm sure you'll start to learn as you guys start getting your driver's license, you need to have those objects strapped in. In fact, yourself as well, when you're driving in a car, you need a seatbelt, because when you're driving in the car, you and the car are moving at the same speed. You are in motion. When you stop the car, your body will continue in motion, will continue moving in a straight line unless something acts upon you and forces you to stop. If you don't have a seatbelt, the thing that's going to force you to stop is going to be the steering wheel, the windshield, and the wall behind the windshield. So if you have the seatbelt will actually give you that necessary force from moving forward. That and the airbags. Again, this is just another commentary of Newton's first law. Again, objects will keep doing whatever they're doing. If an object's not moving, it's going to stay not moving unless you force it to. If an object's moving, it's going to stay moving in a straight line unless you force it to. The main idea actually is that as long as the forces are balanced on an object, the acceleration on that is zero. Now, there's actually a mistake here. I didn't make this graphic, but the unit for acceleration is wrong. But the idea is the same. So here's the first question. Pause the video, work itself. We'll go over in a second. All right, so they want to know which one has the greatest inertia. Well, remember, we're going to cross out the word inertia and write mass. So which one has the greatest mass? 1, 3, 2, and 4. It's going to be this one. Remember, they're going to throw these speeds at you to try to trick you. Right now, you don't really know the equation that would deal with speed and mass, but don't worry about it. Inertia is mass. All right. Now, there's another part of this law. Now, the law is objects in motion tend to stay in motion. Objects at rest tend to stay at rest unless acted upon by an unbalanced force. We talked about the inertia aspect, that objects will keep doing whatever they're doing unless you force them to. This second part actually focuses on that second part of that statement that says unless acted upon by an unbalanced force. So this leads us into this idea of equilibrium. You know the term equilibrium from other science classes. It basically means balance. It's a state of balance. We're using that same idea here, but in terms of forces. So basically what this says is that If the forces are unbalanced, if there are forces that are acting stronger in one direction versus another, then the object will change its motion. If the forces are balanced, then the object will be in this equilibrium and it'll either remain at rest or continue moving. All right. So this is the main thing that you want to know is that equilibrium could mean either at rest or moving with constant velocity. This is something people forget a lot. They think that they relate equilibrium with at rest, but they forget that an object technically could be moving and still be in equilibrium. Because remember, Newton's law is saying that objects will keep doing whatever they're doing. The main reason why people sometimes have trouble with this is if you try to imagine something that has no forces on it, you would think of something like taking your calculator and sliding it across the table. Once it leaves your hand, you know that the calculator starts to come to a stop. And you might think to yourself, there's no forces acting on it because I am no longer pushing it. There's nothing pushing it forward, therefore it comes to a stop. But there is a force acting on that, another force that you're not taking into account: friction. So the calculator in that scenario is has unbalanced forces. Therefore, that's not an equilibrium state. A better example is going into space. If you go into space where there's not really other forces that could act on you, and you start moving an object, it will actually continue moving in a straight line until it starts interacting with the gravity of other planets. It can be a little hard to remember that, but you just have to kind of realize that the moment you see either the word equilibrium, at rest, or constant velocity, you know that all this stuff is true. That if an object's in equilibrium, it's either at rest or constant velocity, and if it's either at rest or constant velocity, it is in equilibrium, and therefore, in those cases, the forces are all balanced. All right. Now, the total force that acts on an object, we actually call it the net force. And the net force is what we call the vector sum of the forces. Oh no, vectors again. This basically means that we have to take into account direction. If you have a force going to the right of 4 newtons and you have a force going to the left of 3 newtons, the net force is what happens when you combine these two. We take the vector sum. This is going to the right 4, this is to the left 3. So we actually have to subtract them because they're in opposite directions. So the net force in this case would be 1 newton. 1 newton to the right. Now, you probably won't have this scenario, but for the most part, you want to make sure that the sum of the force that you do some of the forces in the y direction and some of the forces in the x. Just like we did before, you can't really combine a horizontal force and a vertical force, a horizontal vector and a vertical vector. You kind of want to look only at the horizontal stuff at first and the vertical stuff next. We'll end up dealing with that stuff later on, but the main thing is that if either the y side or the x side does not end up equaling 0, then the object cannot be in equilibrium. So it's only in equilibrium if it's balanced horizontally and it's balanced vertically. Most of the time, there's only going to be one direction where it could be unbalanced. All right, so here's the next set of questions. Pause the video, work itself, and we'll go over in a second. All right, so here we're looking for objects that are in equilibrium. Now remember, the main thing to be in equilibrium is that it has to be moving at a constant speed or at rest. So a ball dropped from a building, a ball dropped is going to accelerate and increase speed. So this is not in equilibrium. A ball thrown into the air, again, it's experiencing the acceleration of gravity. Its velocity will change. Therefore, it can't be B. A kid rolling down the hill with an increasing speed. Again, increasing speed, that's not it. We're looking for constant speed in a straight line. D, a car on a straight highway on cruise control. If you don't know cruise control, that's something in a car, basically keeps you at a steady speed. So D is going to be one of our equilibriums. E, a book sliding to a stop. Again, this speed is changing. F, a stoplight hanging at rest. They say the magic word at rest. So you know F is here. Now here is the next one. G, the Earth orbiting the sun at a constant speed. It does say that the speed remains the same, but again, there was a little stipulation about it having to move in a straight line. The Earth goes around in a circle around the sun. So this is not a straight line. Therefore, this is not what we would consider in equilibrium. So the only cases that are in equilibrium are choice D and choice F. Here's the next question. Pause the video, work and stuff. I'm going to go over in a second. All right, so they want to know which Bach represents equilibrium. Remember, equilibrium just means balance forces. Now, you're going to see these types of diagrams a lot. These diagrams are called FBDs. They're something that we're going to end up learning how to make in a bit. They're very important, something that you definitely need to make sure that you are able to do. FBD stands for free body diagram or force body diagram. Basically, it shows you all the forces on them. So if we look at here, we're looking for forces where they're all balanced. If we look at choice 1, the horizontally is balanced, but vertically it isn't. Choice 3, balanced horizontally but not vertically. 4, not balanced in any direction. D is the only one where it's balanced vertically and horizontally. So choice 2. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so they want the net force acting on the block. We have 8 newtons going to the left, 3 newtons going to the right. So because they're going in opposite directions, we subtract them. 8 minus 3 gives us 5 newtons, and let's add in the direction left. All right, and that's it. I'm going to try to sneak this in really quickly and try to go through this quickly. Drawing FBDs is extremely important. It makes doing a lot of these problems very easy, and it makes it important to be able to tell whether an object is in equilibrium or not. So there's a bunch of forces that actually appear very regularly. There's a worksheet where you'll kind of see all the forces, but I'm going to go through some of the main ones. So the first one that comes up almost every single time is the force of gravity. It can be represented as F sub G or W. And it always acts on an object unless said otherwise, and it always acts downward towards the Earth because gravity always pulls objects down. So if you have an object and the Earth is underneath it, gravity will always pull it down. The normal force, which is represented by Fn, is a force that comes up when you are in contact with another object. This could be anything like a floor, a wall, anything like that. And it always acts perpendicular to the surface. So for example, if I put my hand, pretend that's my hand, and I put it up against a wall, I'm going to feel a normal force coming from the wall, and that normal force will be pushing me away. So the normal force always acts perpendicular to the surface and always pushes objects away. If you look at your table right now and you have something sitting on your table, that table is exerting a normal force pushing it up in order to keep it from going downwards. Those are two of the main ones. Like I said, there are other ones, but we'll kind of cover them when we get closer. And that's pretty much it. Like I said, you have a worksheet where we're gonna go over how to draw FBDs, and you'll practice some of that. And that's pretty much Newton's first law: the law of inertia, the concept of equilibrium, and being able to draw FBDs. If you have any questions, please feel free to let me know. Make sure that you're filling out the notes. If you come in class, you should end up getting the note packet for this, so you should be filling that out. Otherwise, you can either download or print out the note sheet that I posted on Canvas. If you can't see it, let me know and I'll send it to you or guide you towards it. If you have questions, send me a message on Remind through email, preferably Remind though. And make sure to join the extra help if you need a little bit help. All right. See you later.